the second finality for the Ethereum consensus client. Last time we had been talking about Casper FFG. We will continue talking about that, but last time we were mostly focusing on the two-step commits and slashing. And today we'll be talking about a couple of more things, which are k-finality. We will be looking at all of the code on the specs that's related to this, and also to the things that we saw last week or a couple of weeks ago. And then we will see what can go wrong, or one specific case where finality was not happening and how did that get fixed. So before I start, let me just go search for the YouTube link so that I can share that everywhere and people know we're doing this. I will share in Telegram. All right, it's being shared. So where did the finality? I think here's the slides again. Okay, that's perfect. So let's start. The first thing we will be talking about is k-finality. So just to review, one of the things that we talked about last time is that Casper FFG had a two-step commit mechanism, right? We usually, every time we send an attestation, we send a link basically between a source checkpoint and a target checkpoint. So I'm voting for two things at the same time. The source is basically what is my last justified checkpoint, and the target is what I think is the current checkpoint that is not justified or anything like that, right? So one of the things that is very important in this is that the only way that I can finalize something is if I get a supermajority link, which means that 2/3 of the people emitted the same link, to 2/3 of the stake, actually, because this is not about the number of validators, but also about how much stake do they have. We'll see how validators can have less than 32 ETH in a little while today. And one of the important things about this is that that's not the only condition. There's a second condition, which is that to finalize something, we also need the source and target checkpoints to be consecutive, right? So this is the two possible scenarios that I can have. The first one is where the source and the target are consecutive, and there's a supermajority link, and that's why I have 2/3 here. And then this finalizes. I will use this light blue color as a finalized epoch, right? And there's a different scenario where we can have a supermajority link like this one. Like I had this source, I had this epoch justified, the following epoch justified, and then I will, if I receive this supermajority link, I will get this target justified, but this will not get finalized because there's a gap in between, right? That's how it works. So this can introduce one problem, which is in an extreme scenario, there's a possibility that I will never be able to finalize. Like I may be justifying each individual block one after the other, but they still wouldn't get justified. And this is one possible. Sorry, I think that you might just lost the last second. So I was mentioning that this was in Benedict's to book. This scenario was described there. This is just like a little Google Slides animation. Well, animation is an overstatement, but whatever. What I mean is here we can have the way in which this scenario can be produced is when you have a delay in attestations, for instance. So maybe I attest for a specific epoch now, but instead of that being received by every validator and then being included in blocks, it may be the case that for some reason the network is slow, for instance, those attestations arrive in the next epoch. So what I will be representing here is 3 steps in one. So I will first receive some stuff, I will apply some stuff here, and then I will send something. So let's assume that we start with this as my current justified checkpoint, right? And this is the epoch that we are currently transiting. Like this is where we are at now in terms of time. So what I will naturally do is that I will emit a vote from this justified to this target epoch, right? This will be my attestation, and I will send that to the world. In the next epoch, the target epoch will be this one. But I didn't, as attestations are delayed, no one received my attestation, so this one didn't get justified. We still have this epoch, it's just not justified, because if we remember, to justify something, I need to have received a supermajority link pointing to it. Or in other words, I need to know that at least 2/3 of the network attested for that to be in the current epoch. So what happens in the next epoch? Like I already sent this, and then I sent this one, because the source doesn't change. The source is still as justified checkpoint. In the next epoch, I will receive the first message because there was a delay, right? So the first thing I will do is I will finalize this one, because these are two consecutive checkpoints, and this one is justified, and this one was already justified, so it now becomes finalized. So now I will emit a new vote from this one to this one, because this is my current target epoch. The problem is that this is the only attestation that was emitted for two consecutive blocks. The next one will basically be from the first one to the third one, and I will justify this one. But there's already a gap here, so now I will emit an attestation from this one to this one. And this keeps happening infinitely. And if you can see this correctly, basically I am justifying one epoch in each step, but I will never have two consecutive ones, so I will never be able to finalize anything. Any questions until now?
I'm actually lost. I don't get it.
All right. Did you did I lose the connection, or or is there a part of the explanation that we want to go over again?
Yeah, like at the point where like the blue part came in, like I don't understand it.
Yeah. So blue is finalized and orange is justified, right? Just to review from last time, um, justified means that I received attestations. Like the process is that I first let's review the process a little further back. So the process is someone proposes a block, right? And then attesters see, hey, this is a block being proposed, and they attest to it. And they emit two kinds of votes. On the one hand, they emit the fork choice vote, which is this is the current proposed block in this particular slot. That's for fork choice. But they also emit a different vote, which is their Casper FFG vote, right? And that includes two checkpoints. That includes the checkpoint for the current epoch, like, hey, this is the root of the first block of this epoch. That's the target. But they also emit another one, which is called the source. And the source basically means, for me, this is my last justified one. Now, let's remember what justified meant. Justified meant when every validator, every attester sends their attestations, then those attestations are received and propagated by the rest, right? And something that happens there is that when I sorry, lost connection for a second there. When I receive 2/3 of the attestations saying that this is the current epoch, and they all say the same thing, then I say, okay, this epoch for me is now justified. This is the root, and I will never revert it. I commit to never reverting that. Finalizing is knowing that the rest of the people have also justified that block, because at that stage I may be the only one committing to that block. At that stage I received 2/3 of the votes saying, okay, yeah, this this is the epoch for us. But they may not have received the same messages that I did, right? And if they didn't receive the same messages, then that means that I will have that justified, but the others wouldn't. In terms of what my validator does, it's the same thing. I already committed. I won't be able to go back. The difference is that finalization means that not only I have justified that, but 2/3 of the network have justified that. And finality is not a local property. It's not a property of my node. It's a property of the whole network. Justification is self-commitment, is I won't ever revert this. Finalization means not only I did that, but I can guarantee that at least 2/3 of the network cannot revert that. Right? So that's, and finally, if you look at the specs closely, finality is not used basically anywhere. It doesn't change the way in which a validator behaves. It's mostly information for users. Users can, if users know that something is finalized, they have a certain level of guarantee that it will never be reverted, at least without what we saw last time, which is at least without 1/3 of the full Ethereum stake being burned, slashings, etc. But if we're in a honest network, we know for a fact that it won't be reverted. So finalization, as it's a global property, it's a network property, it brings real guarantee to users. Justification is only self-commitment. And finalization is making sure that at least 2/3 of the people, of the validators, have the same one justified. Sorry, that's mostly a recap for last time. And let's go back up a couple of slides to make sure that we're on the same page. Taking that into account, this is what we call a link, right? This arrow is a synthesis, meaning this is one single vote that takes this as the source and this as the target. The target is the current epoch for myself. I think this is the current epoch, so this is the when I emitted at the station. This is my vote. And also, this here is the source. And the source means this is, for me, the last epoch that I have justified. So this is the last epoch that I'm committed to not reverting, right? And what happens is that if 2/3 of the network vote on the same link on this source and this target, then two things happen. The first one is that this gets justified and this gets finalized. Right? Are we all on the same page there? Or do we have any questions? Which is perfectly fine if we do, right? That's what the workshop is for. All right.
So,
Yeah.
since the source and target, so you said the source is the last justified for me,
Yes.
and the target is the last epoch, the current epoch. I'm currently saying, right?
Yes. So
Okay, I think the colors are confusing, like they are the same thing.
are
The
like
source and the target.
right. So maybe like if we're being strict, this for now shouldn't be orange. This should be gray. And after applying this should be blue, and this should be orange. Let me just quickly fix
Okay.
that actually, because I do have. Oh, I stopped sharing. I didn't mean to do that. I only wanted to stop the slideshow. Oh. So what I will actually do, this would be probably a more correct thing to do. Let's go to the slideshow mode again. So basically, before applying that supermajority link or all of those votes, this is the situation. This is my last justified one, and this is the currently being processed epoch. And after applying that supermajority link, this is the after state. Thanks for pointing that out. That was the colors weren't correct for this like state transition view. So after applying, I get this one justified and this one gets finalized. But this only happens if these two are consecutive. If I have something in between, the rules say that this cannot be finalized. The only thing that happens, I didn't include it here, but I will. This can be. Sorry. Let's just quickly edit this. Oops, something like this. And what will happen here, we're testing in production, guys, is that this will get justified, right? So the effect is that in this case, one thing gets justified and the other gets finalized. In this case, there's justification but no finalization. Why? Because I have a gap. And normally, what the specs intend is that you only finalize if you have supermajority links that are consecutive, that where the source and the target are consecutive epochs. All right, and this is mostly to avoid, like, I should do more in-depth reading on this topic, like why we only want consecutive ones. But what I think is that this basically avoids stuff like me getting a very old thing that's finalized thanks to justifying something new, and then in between there's a lot of things that could be in doubt. So this is the classic finality, but we will design a different finality that takes this kind of cases into account. So as we saw, we have a big problem here, which is network delays. This is not a normal network delay. And we are modeling this as a delay, but it could also be that validators are offline and I'm just not reaching a supermajority link. What we are saying is that for some like strange reason, we're receiving attestations a couple of epochs afterwards, which is extremely weird, right? Like you should receive attestations in maybe in the next slot, like whenever they are included in a block, maybe the next slot, the next two slots, but an epoch. Let's remember that um, these gray or orange or blue blocks, these are not blocks, these are full epochs, and these are 32 slots. So I should be receiving a lot of attestations during the whole duration of the epoch. So it would be like a very extreme case, but it also happens sometimes, not exactly due to network delays. It happens due to another reasons, like people going offline, for instance. What does happen is that we may get not this, because this one is correct, right? This is my last justified one, so I'm voting for this and this. This is my source, this is my target. But the problem is that other people are not receiving this. So what happens is in the next epoch, I will vote the same thing. This is still my source because I don't have any new justified epochs. But the target epoch changed because now I'm in a new epoch. This is, and now this is the first vote. Now everyone received these votes because there was a delay, but everyone received it. And I can finalize this because the gap here is just one. But here, and this is what I'm sending, right? This is what I'm receiving. Maybe the graph is not the clearest one. I will rethink that for the next edition of this workshop. But what keeps happening then is that I will keep receiving votes that have a gap. And mind you, this problem is only happening because there's a constant delay. In a real life scenario, eventually that delay would stop and I would start getting these kind of votes again. Because my view of the network would catch up with the actual messages being sent. But this is a real problem nonetheless. Like, hey, we are actually justifying everything. Why can't I not finalize something? Because like it's true that you don't want to finalize something is there like if there are like gray gaps in the middle. Because if there are gray gaps, that means that nothing here is justified. Like the network's definitely not agreeing on this. This like justification means that at least 2/3 of the validators voted on this being the current epoch. So that's a pretty good level of confidence. So what they invented for this is k-finality. K-finality is kind of a relaxed finality where they also allow to finalize a block if an epoch. They allow to finalize an epoch if you have uh, epochs that are justified in between. And Ethereum uses k equals 2 or 2 finality, which basically means that we cover this specific case. Like if I have a source, I have a justified epoch in the middle, and I have a target epoch, then in that specific case, I can finalize the source. If this was a gray epoch, like if this wasn't justified, or if there were more epochs in between, then this wouldn't be able to finalize. But for this specific case, it does. And if we went back to the same example as before, that means that in this example, this would get finalized, for instance, and we wouldn't have the same problem. With this is a perfectly normal blockchain. The only problem it has is that it has some level of delay, but everything's getting justified. So again, interrupt me anytime that you have doubts or questions. So basically, this, like, originally we only had this possible case for finalization. This is the original case where we have a supermajority link for 2 consecutive epochs, and then let's always think that the last one is the current epoch, right? So I will justify this one, I will finalize this one, and that's it. That's the classic only way of finalization. We call it one finality. But here we are all like 2 finality basically accounts for delays. So when I'm reviewing, I will review not only the current epoch, I will also review the immediately last epoch, because I could get delayed votes on this one, right? The timely votes will be votes for this one as target, but I will also maybe get votes for this one, and this may be just justified. It may be justified in this particular, after processing a single block. So in this case, if this was my current justified, then this gets finalized, this gets finalized, this gets finalized. Sorry, these 2 get justified, and this one gets finalized. And this is applying to finality. Then there's 2 more cases, because if we are taking into account delays, then what could happen is that I justify this one. I don't care about this one, but I justified this one, which is the previous epoch. And it could be the case that when I was processing things before, I didn't justify it because I didn't have all of the votes, but now I do. So what we do is we not only save the current justified, but we also save locally in the state, in the beacon state. We also save what was the previous justified before that one, so that I am able to perform one finality on these 2, which are not the last 2, but the previous 2. And then this is basically the same thing for 2 finality. So these are the 4 cases that I could encounter. When we are actually processing this in the code, we will go through that in a minute. We'll actually do all of the way around. The only reason why I covered this first is because this is like the simplest case, the classic case. This is like just delays, and these 2 are a little bit more complicated, right? They are delays, but also for a previously justified one. But in reality, we will perform this one first, then this one, then this one, then this one. I think that who was working on this? I think that Akash was working on this originally. And the reason why we go this one, and then this one is because if this gets finalized and then this gets finalized, that's no problem. Because if this is finalized, everything that's before is already finalized. So basically, if I do this one, this one, this one, and this one is computed, I will just finalize this and this and this and whatever. So basically, when you finalize something, you also finalize every epoch that goes before it. So any questions until now? Being completely lost is also valid, because this is a tricky section. Okay, so now let's go to the code, where we will apply everything that we saw last time and this time. So this is epoch processing. We will not go into everything that's done at the end of an epoch. We will only be going into this one for now, which is processing, justification, and finalization. So the first part of processing, justification, and finalization is mostly getting state. It's getting stuff, right? So the first part is just excluding genesis. Like, we don't want to process FFG votes in the first 2 even, because if you remember correctly, we need a couple of previous states, and if we are just starting from the beacon chain at its beginning, we will not have previous, like, attestations for previous blocks and stuff like that. But this is an if that's completely irrelevant now, unless you have an archive node or something like that. And what I will collect here is a couple of different values. I want to see here with previous indices and current indices. Let's always, when you read indices, we're referring to validators, right? These are validator indices. And what we're getting is timely target flag index is basically what means that a validator. Sorry, I will explain what this function does. This is probably the best thing to do. So we're getting validators that are not slashed, so are participating in consensus, because slashed validators do not participate. And we're also getting, this is a filter that we apply on those. It's a filter saying they not only participate, but they participated in time. So their attestations got included into blocks quickly enough so that I can, if I emit an attestation, but for some reason it gets included like 3 epochs from now, I will not be into this list because I will not get rewards for that. So with previous and current, I'm saying these are the validators that emitted attestations that were valid and also in time in the previous epoch. And this is for the current epoch. And the reason why I'm doing this is so that we can compute this kind of stuff. We will add votes for here and for here, for the current epoch and for the previous epoch. So I'm basically catching votes for the last 2 epochs here. For here, we're just getting their indices. And then what I will do is get their total balance. Because if you remember from previous mentions, we don't care about the amount of votes. We care about how much their added stake weights. So that those are the real votes. If, for instance, I have 15th because I have been penalized for stuff, and then Fernando comes in with 32th, his vote will be weighted as double of mine. His vote will be more important because what votes here is not individual validators, it's their stake. So here what we do is convert those indices to stake and nothing else. So we reduce these arrays to a single balance. And then I also get the total active balance, which means because what I will care is to calculate 2/3 of something, I need to know what the total is. And you could be able to say, hey, this is the current total balance, but what about the current, like the total balance for last time, right? Because maybe let's go back here. Like it's very easy to see if here we have 2/3 of the stake. But what about here? If I want to justify this, how do I know this was 2/3 of the stake? Well, there's an approximation that we use where we say, hey, the last time and this time, the total balance is the same. Why so? Because there's a kind of a limit to how much the balance can change between 2 different epochs. And that has something to do with how validators, how rewards, penalties, and also slashings and deposits work. There's a hard limit on how much that can change. So we just can approximate that. And then basically all that we did in all of these lines is get balances, get these 3 balances, the total, the voted in the last epoch, and the voted in this epoch. And then we can just delegate to this function, which actually applies justification and finalization. So I divided this into several slides. The first thing we do is, well, getting which epoch we are in now and which epoch we were in the previous state. And we save the currently justified and the previously justified checkpoints for this state, right? Why do we need the current and the previous? We need the current and the previous for this, because this will be my currently justified, but maybe I also had justified the previous one. And if I justify this one, then I will finalize that one. So I need to save both of those things. And then after saving both of those, I do a couple of things. The first thing that I do is justification bits is literally this. This is justification bits. It's an array of 4 elements that is either true or false. And it's represented with a bit vector of 4 elements. And if it's a 1 or true, it's justified. If it's a 0, then it's not justified. That's it. It doesn't track finalization or justification. So first, what we do is shift up. Shift up means basically I should have already a graphic for this, but if I had like 0, 1, 1, 1, I will have 0, 0, 1, 1. Like I move everything to the right. And moving everything to the right basically means I'm accounting that I'm in a new epoch now. Like what previously was my first epoch now is my second epoch. And the lowest index represents current epoch, and the first index my previous epoch, third index the previous of the previous, etc. So shifting up basically accounts for the passage of time for one epoch. The next thing that I do is I justify the previous epoch. If actually the two-thirds of the votes are reached. So what I see is, hey, the previous epoch target balance, which was like the people that voted for the previous epoch, is that two-thirds of the total active balance? If that's the case, then I justify it. And I set the justification bit of the previous epoch, that's why the index 1, I set it to 1. So I basically say this is justified. And this is part of the state. So I'm modifying the state. This is part of the state transition, right? And then what I will do is I will do the same for the current epoch. So instead of previous epoch target balance, I use current epoch target balance, which is the votes that has the current epoch as a target. If this balance is two-thirds, at least two-thirds of the active balance, then I will justify this one. And by justifying, I mean I take the first justification bit and I put it as 1. And that's justification. Justification is relatively simple. The data structures are kind of weird, but the justification itself is simple. Is the amount of votes is larger than two-thirds. That's it. Finalization, it's the tricky part. So let's go over it. I try to separate this into several slides with like Google Slides animations, if that's a valid thing to say. So the first thing we do is this. We say all bits 1 to 4 are present or are 1. This is a very weird syntax, but what this means is this. These 3 are justified. See, 1 to 4 means this is 0, right? And I put 0 in the right because this is the current epoch. So this represents time, and this is 1, 2, and 3. 1 to 4 in Python doesn't include the last one. So this is basically 3. The reason why it is like this is because basically they want you to be able to do the subtraction 4 minus 1, and that should give you the amount of elements. So if you do 4 minus 1, that's 3 elements, 1, 2, 3, right? And then we see that the old previous justified checkpoint plus 3 is the current epoch. What that means is that this was the old previous justified checkpoint. And if that's the case, it means that I had these 3 justified and that this was the last justified in the previous epoch. That means that I can finalize that one, because it means that this is my source, and this was my source in the last one, and this was my target, and these 2 are justified. So I use to-finality and justify this one. The next case is this one. It checks if bits 1, 2, 3, so 1 and 2, 1, 2, are justified, and also if my old previous was this one, which is current plus 2, current 1, 2, right? And if that's the case, this is the classic one finality, like these are consecutive, but for the previous justified. So with a delay in I just justified this one. So this will get finalized. This is a third case, which is I'm now seeing the current epoch as the target, but and now I'm using the current justified checkpoint as this one. This gets finalized as well. This one was to-finality for the current epoch, and this is one finality for the current epoch. So I will get this justified as well. I basically added these representations because they are a bit easier to understand than these kind of lines where you see all of these bits to 1 and also all previous justified plus 3, but they basically represent these states here. And these are the 4 cases of finality that we saw a little bit earlier. So what this code does is basically this. It models this that we talked a little bit before. So I think that the most important takeaway of this is that for finalization, we use to-finality, and to-finality means that we can skip 1 in the middle if it's justified. and if that's the case, then we can finalize the first one. But I need to account for delays, right? Because that's the whole goal of two finality. This is the classic one. If I get delayed votes, I may have this case. But if I am really accounting for delays, then I am also need to take into account, hey, what happens if I have just justified this one, but the previous final justified checkpoint was this one. I should finalize that as well. So these are the four cases that I should take care of. And if none of these cases happened, then I just don't finalize anything because none of the four possible conditions of finalizations happened. All right. Any questions until now? Cool. We have maybe 7 more minutes, and we have like 2 or 3 more sections in today's workshop. We have slashing code, which is very quick. We also have inactivity-leak, and then we have the case. I have 2 options. We can end up on time, and we can you can decide what you want to prioritize, or we can just go forward and maybe we take 10 more minutes. What do you think would be the best? All right, I got at least one message saying I will need to leave on time, so I will exactly do that. Let's review the slashing code, and then we can decide how far we go. So for slashing code, this doesn't happen in epoch processing, it happens in block processing. Why so? Because the attestations that we use for Casper FFG are not the ones we receive in Gossip, they are the ones that we receive in blocks. So when we are processing blocks, then we process the slashings. And the same with slashings. We don't care about, like, for now, we are not putting ourselves in the step of a validator that monitors and generates slashing proofs. We're only processing slashing proofs that were included in blocks, right? So it happens in this part, which says is slashable attestation data. And what this does is literally what we talked about last time. There's double votes and surround votes. Double votes that shouldn't happen is when data one and data two are attestations. So if I have 2 different attestations and the target epoch is the same, that's a double vote. It's not respecting fork choice. And if I have a surround vote, which means that one is surrounding the other, literally this source is higher than this source, and this target is not higher, but lower than this target, it means that data 1 is surrounding data 2, and that means that they're not respecting their own justification votes. So in any of those cases, we need to slash them. And now we go to inactivity-leak. Let's be very quick about this, but I think this is one of the most interesting parts. I think that last time it was Mete that asked me, hey, what happens if we, or God's Power, I don't remember, what happens if we don't finalize? So like how to recover? And this is one of the main mechanisms. So inactivity-leak is supposed to protect you when at least 1/3 of the network goes offline. Because if 1/3 of the network or more goes offline, that means that you will never be able to justify or especially finalize blocks, right? And that's a problem. That's a big problem. So what happens if we don't finalize the network for a long time is that we will start we enter a mode called inactivity-leak, and the inactivity-leak has 3 consequences. The first one is that attesters receive no rewards, and attestation penalties remain the same. So this is an incentive for attesters to try to fix the problem. Because if I have a working node, I will. If I didn't have this one, I would say, okay, like offline people are getting penalties. I'm not getting penalties. I don't need to do anything. So this is an incentive for everyone to cooperate on this. Inactive validators receive penalties that grow quadratically over time. This means that at first I will start slow with slow penalties, but then those penalties will start rising. And proposer and sync committee rewards unchanged mean that people that propose blocks still have the same rewards. So why does this work? Mainly because if this is a situation, I have like this amount of validators that are online and these are offline, and I add a penalty to this one, the proportion changes, and now these are 2/3 and the network works again. Again, in Altair, the quadratic score was added, and this means basically because before Altair, basically everyone would be penalized the same way. And the problem with that is basically that um, the main problem with that is that it's very hard to consistently be online when the network is chaotic, right? So this basically means if you miss maybe a single attestation or a single block while there's an activity leak, you will not get penalties that are very high. But if you are like consistently offline, your penalties will be very, very high. And the way that this works is that you have an inactivity score. Basically, the two things that can happen is if you're active, then your score lowers in one, and if you're inactive, your score goes for higher. And if we are not in a league, then everyone's score, even the offline people, will go down. But you don't get penalties if you're offline now or online now. You get penalties based on your score. So if you have been offline a lot in a league and then the league stops, then you still will get penalties. So let's go to the code, right? There's processing. This is in process epoch again. It is process inactivity updates. This will just update the scores. So basically, how does this work? The first thing that we do is we check which are the validators that are eligible for penalties. So they can be either active. Active means that they are not slashed, or they can be slashed but not exited, which means that they were slashed but they didn't like get the remaining Ethereum out of their wallets. So they can still have penalties. Well, these are the once we filter the eligible ones, we basically do this first part, which is we reduce the score if they participated, right? So how does that work? We see if the index is in the unslashed participating indices. Participating again means they emitted a vote. This is the same function that we use for Casper FFG. We check if they emitted a vote, and if that's the case, and if they emitted a vote in a timely manner, then we will reduce their score by one. In any other case, like if they didn't participate, then we will augment that in four. This is this always happens, but aside from that, we also check what happens if there's an inactivity leak. If there's an inactivity leak, then if we are outside of an inactivity leak, which is 4 epochs, like if inactivity leak means 4 epochs without finality. If that doesn't happen, if we're outside of it, then we'll reduce everyone's score by 16. And there's a separate part just after this, just after processing the updates, which is processing rewards and penalties in general, right? The rewards and penalty includes other things, which are called flag deltas. Here are rewards for timely inclusion of your attestations and blocks. And then we add the inactivity penalty deltas to the delta list. And then eventually we apply deltas means positive delta is a reward, negative delta is a penalty. And basically we apply all of those here. But let's go into the inactivity penalty deltas. How are these calculated? So basically, this is a lot of code, but let's go line by line. The rewards will always be 0. I will never get any kind of rewards for this. The only reason why this is here is because we need to return both rewards and penalties, but this is a 0, right? The next I will do here is I will calculate the matching target indices, which means which of these are unslashed and participating. And if someone is not participating, basically, and is also eligible, I will basically apply the inactivity leak penalty according to their score. And this is the most important part. This is the calculation. So basically, I will calculate their balance and I will multiply that by their score. So basically, I will get their balance deduced using their score. And then I will apply the penalty here. So that's inactivity leak. So what we learned here is that people get penalty proportional to how much time they spent offline. And this is a story, a very short one, that happened last year. This is the only time where the Ethereum network had problems with finality. So this is a very short version of what happens. There are postmortems that are more in-depth online. But what happened was basically this one. The network was already under stress because they were processing many deposits, like the validator set was increasing very fast, and that already puts like stress into the network. Then what really happened, what really triggered the issue, is that there were many attestations to all blocks that were at least 2 epochs old, right? Which is a normal behavior. It's something that can happen. It's not something that happens all the time. It's not frequent, but it's normal. It doesn't mean that there's any dishonest behavior happening. And this is something that, for instance, Lighthouse might do when their execution client is not working, right? For instance, because if I'm not validating new blocks and I'm like really behind, I'm like 2 epochs behind, and I get to propose a block, sorry, I need to attest. My attestation will have as target what I think is the current target, and that will be maybe 2 epochs old. Not a very common thing to happen, but someday happens. The problem is there were not many attestations like this, but there were enough. And the issue is that if you need to validate an old attestation, some of the clients need to revive all beacon states. And we currently save all of them in a DB, but that's extremely costly in terms of space. And what other clients do for now is that they don't save all of the states, they just save some of them, and then they recompute the states. The problem is that because of the size of the caches where they had the states and that kind of stuff, and they had a problem where they started replaying and regenerating a lot of states, right? Because these were very old. They definitely didn't have this on cache. And the cache was not big enough. So basically what happens is something that's called trashing. Trashing is when you fill a cache and then the new element replaces this one, but then you needed this one. So this one will replace the next one. So basically it's the worst case. It's when having a cache is worse than not having it. Because basically you replace an element in the cache and you never hit and you always miss. It's basically the worst case that you can have. And what happened here is that clients like Prism and Teku encountered this issue. They started getting cache thrashing, and they started getting resource exhaustion, which means that their CPU and memory started getting too high. And that CPU memory and CPU and memory usage was so high that they stopped being able to address current things. They stopped being able to fulfill their attestation and proposal duties. So virtually, it happened as if they were offline. They weren't offline. They were actually processing so much information at the same time that they weren't able to process the current information. So basically something seemingly innocent, like all the stations, broke a couple of the clients. And what happened? Let's remember that this is now. I don't remember how it was exactly last year. Could have been very different. But Prism and Teku together are almost 2/3 of the network. At that period of time, maybe a little bit more than 2/3. And what happened is, well, this is the bad news. A big part of the network went offline, more than 2/3, so finality could not be reached. There were not enough attestations, and there were also many attestation and block duties that were not fulfilled. So there was a lot of missed stake. Maybe there was about 50th that was lost. Not lost because it was burned, but lost because it was not gained by the validators in their normal duties. And they were about, there were 2 inactivity-leak periods, one for 4 blocks and then one for 9 blocks. And then there were 3 validators that were slashed. We don't know exactly why, because those are private things. We don't know anything about the real lives of these 3 validators, but what's suspected is that there were probably operation errors. That there were probably someone switching from one client to the other, and in between generating a DB problem that produced slashing behavior. The good news is that Lighthouse was working correctly through all of this. They basically dropped all their attestations and just continued with the current chain. And that means that the chain was able to go forward as if nothing happens. Like people were being able to interact with the chain. The problem here was finality. This was not network downtime, which is amazing. Like even with this like gigantic issue, Ethereum still kept working. So new blocks were still getting proposed and attested for, and fork choice still worked. So there was no Ethereum downtime, and there was no significant rise in gas prices. So what happened afterwards? Basically, the problem fixed itself, which was awesome. Basically, the inactivity leak worked. The working clients continued emitting uh, proposing blocks and attesting for them. So the network continued to work, and eventually the Prism and Teku got out of their trashing states, and they didn't need to emit any kind of bug fixes. They did add some bug fixes afterwards, so that the probability of this happening is way lower. Prism added a bug fix, which is they started using the head state for attestation validation instead of needing to regenerate whole state. But also both Prism and Teku started discarding old attestations or attestations for unknown chains, which is almost the same thing. So this never happened again, fortunately. These are a couple of sources. So if you want to read a little bit more data on that, especially the first one, this is by Off-Chain Labs, which is the owners of Prism. It's a very good report, and it's what they based their fix on afterwards. And that's it. That's all, folks. That's all of Finality. It was a big topic. We needed 2 workshops to cover it. I also really recommend everyone to go and actually read the specs after this. This is a very detailed thing, and it took me more than I am happy to admit to understand some of these concepts, especially the 4th state of finality. That one for me was the most the trickiest part, because you have to take into account the current epoch, but also the previous epoch as if you had a delay. So yeah, do we have any questions? Anything we would want to expand on? Anything we want to go back to?
No, everything was clear. I had to check again the video, but
Yeah. Feel free to
the
rewatch
password.
that.
Yeah.
Thank you. All right. If we don't have anything else, thank you everybody for coming. This is probably the last workshop in a while, so thank you for attending all of the workshops. Thank you for your questions, for your participation, and yeah, we'll see you all on the next one.
Bye.